Hello everyone, I'm Troy Schmidt from Geoprobe. I'm here today to talk to you guys about the electrical conductivity or soil conductivity system. The intent and why you would use this is to identify soil type, of course, but ultimately you want to quickly classify a site by soil bearing zones and to speed up the process of sampling or placing wells. Our philosophy is this: without soil conductivity producing a map of the soil, we really are probing blindly and not sure what we're going into or where we're placing our wells. So we like to do a soil conductivity log or electrical conductivity log before every site investigation. Typically, the main principle behind this is every soil conducts electricity differently. So the primary factor is soil type, soil makeup, and grain size primarily. So the three parameters would be first and most important is grain size, determines soil conductivity. The second is material makeup or mineralogy, and the third is pore fluid. So in that order is usually why you see a change in conductivity. So anytime we see an increase in conductivity, we say that's a decrease in particle size. First is the field instrument. We call this the Geoprobe field instrument or field computer. It's simply the logging system and the backbone of an electrical conductivity system or any of the other products we use at Geoprobe for direct measurement of soil properties. And so this thing runs the program and acquisition that collects the data. The first thing I'd like to talk about, and I mentioned electricity, but really we're talking about a low-level signal. The principle behind this is the upper and lower poles, we induce a electrical current into the soil, and we get back a measurement of voltage and current, and we can measure conductance. In doing that and calibrating a probe, we then run a correlation and identify a conductivity. The SC400 probe is the one many people use today with 1¼ inch rod systems. So both of them you can see are about 1 foot long. This one's 1½ inch diameter, connecting to 1¼ inch diameter probe rods. This one is 1½ inch diameter on the fattest portion, connecting to 1½ inch diameter probe rods. As with CPT and other tools, anything we do that's an in situ type tool and we're measuring depth, we have to have some device to track depth. This is also called a string pot, and we tend to use this type on direct image type products like soil conductivity. Same case applies as this is mounted on the machine, and as we're pushing, readings are taken to track depth. When we retract, it's in a neutral position and waiting for the next rod to be added. As we begin advancing, we track depth again. So depth is logged to the PC through the cable. Same thing applies as other tools, is that we've got sensors or contact electrodes down hole that receive signal. So ultimately in this system we've got 2 cords that run to the field instrument, one being depth, one being conductivity. So we store those on the computer and can be downloaded later for viewing or editing. The other device we use is a piston weight. Many machines, Geoprobe machines, already have a bracket on the foot. This is a floating type of pin intended to keep the ground as a 0 reference point for string pot measurements. If this were mounted on the foot, as the foot is coming up and down, this is floating on the ground, keeping it a 0 location point for the string pot, so there's no changing there. Got my rods pre-strung, so you can see my conductivity cord is running through the ID of my rods. I've got my conductivity probe connected. I'm using the SC500 with my connecting rod. Located on the other side is my string pot. Once again, same principle as all of our downhole tools, is we have to have a method of measuring depth. So that's mounted up on the bracket and a cord running from it through the hose reel to the back of the field instrument. We use a slotted drive cap. The slotted drive cap is slotted on the side. So because we have a slot, we're able to let the cord exit the rod string. Being that we have a GH60 hammer on this machine, I've got an adapter to adapt to the wider throat of that hammer. Before I get the computer set up, I'm going to push this probe down to the center of the array. Okay, so the center of the ray is the center of the 4 contacts. I'm going to run the winter style configuration here. So now I'm to the log screen. It takes me virtually 15 seconds to get to that point, and I'm ready to log. At this point I'm ready, so I turn the trigger on. Now what that means is that's activating the system, so as soon as I begin advancing downward, I'm going to start collecting whatever the probe sees in terms of connectivity. So I simply unthread or thread the probe rod down the string and make my next connection. I'm now ready to continue with my next push. So I'll continue by adding more rods. And as I'm going, I'll watch my field instrument to make sure I've collected data for every foot that I've pushed, and it looks like I have them. We just completed our push to 70 feet. Now we've done some sampling here before. Now once again, connectivity gives us a clue or an idea about what might be there, but what we generally want to do is follow up with soil sampling to confirm. So the key is few samples, many logs, and at the end of the time we've got electronic files that we can reproduce in many graphic formats. This is the EC or electrical conductivity log that we ran, and as you can see, we plotted a line across the screen here. Conductivity being on the y-axis, depth being on the x-axis. The lower graph is speed or rate of penetration. A couple things I'd like to point out is these peak values here, as we're up in the higher conductivity ranges above, at least above 100 anyway, those are going to be silts and clays. Now we see a little bit of a dip here below 100. This is going to have some sand content. And then beyond this, all of the information past 35 feet are all sands. Now I've confirmed this by taking soil samples of this area previous, so I know what these soil types are. For example, this spike right here is actually a clay lens that's down there at 55 feet. Very useful information for when we're taking water samples or placing a well. So in a nutshell, that's been our rough run through electrical conductivity, or what we call or like to call e-logging.